Welcome back to Calc 2 videos. We are now today looking at 6.3, which is volumes by slicing. So I want to go start with something that everyone is very familiar with, and that's an area of a pretty basic geometric figure. So let's suppose I drew a line, and I'm going to call that line y equals 1/2 x. Okay? And we're going to take that line up to x equaling 4. All right. Now, I want you to imagine kind of grabbing hold of this line and swinging it around the x-axis here. Revolving it around the x-axis. And think about what's going to form if you do that. So you'd end up down here at some point, right? You would end up, again, we're going to swing it around. And as you can see, if you took this line, anchored at the origin, and swung it around the x-axis, you would literally simply have what we call a cone. Right? That's a really bad cone, but you get the idea. Apologize for my drawings not being as good as they can. Oh, I can get the area of a cone by knowing the basic formula, right? You have your circle base, of course, which is pi r squared. Multiply the height, but because it's a cone and not a cylinder, we take 1/3 of that. I want to close them off for a second. Sorry about that. So my cone has an area of 1/3 pi r squared h. I can get all that information off my graph here. Okay, the radius, right? Well, that's simply let me fix this up a little bit. I screwed up my drawing slightly. That's okay. Let me put my 4 here. That's where I wanted it. All right, no problem. So our radius is going to be this value right here. So it's going to be the y value at 4. Right? So it's 1/2 4, which is 2. So I have 1/3 pi 2 squared. And my height, I'm going from 0 to 4. So my height is simply a 4. And I can easily get the volume of that particular cone that's formed. 16 looks like 16/3 pi. All right, that's not difficult. Shouldn't be. How it becomes difficult is if I change my y equals 1/2 x into, say, something like y equals x squared. Up to 4. And I go ahead and rotate that particular figure. As you can see, we no longer have a basic geometric shape that we already have a defined formula for. So let's go back to the one we know, and let's apply some calculus to our cone. So what do I mean by that? Well, we all know what integration is, right? Area under a curve using our rectangles. But let's talk about, instead of rectangles, what if I just make a whole bunch of these circle slices, right? Just tons of them. Tons of them. And I say, okay, my volume now is made up of all these circle slices. So these circle slices, each of them is the area of a circle at some value x, right? We'll call it x, okay? And of course it has a width. right? So each of these circles has a different area. It is dependent upon the x value wherever the circle actually is, right? And if I sum all these circles up, okay, in fact, summing them up, making n of them probably isn't enough. I can do more than sum them. I can take that sum out to infinity. All right, so I said we're going to apply some calculus to our very simple cone. Oh, well, we already know what taking a limit to infinity of a summation is. Well, that's an integral. Okay, between one defined area and the other. Okay, the area of whatever that figure is that is sliced, dx. This gives us what we call the general slicing method. And it's called general because not always will you have circles. A figure can be formed in such a way. You can kind of check out the beginning of the slides I posted for you. And you can see some figures called a parabolic hemisphere. So I encourage you to just kind of look at them for a minute, where your part that's being sliced, that's bound by all these different curves, actually comes out to a rectangle. So then your area function is that of a rectangle, not that of a circle. So this becomes what we call our general slicing method. And we use this to get the volume of a solid. So again, we're a of x, and it represents basically just a cross section, and a of x represents the area of that cross section. Now you'll see in a minute, most of the ones we're going to do are going to be circles. But again, if I refer you back to the 6.3 slides, the very beginning slides kind of show a rectangular cross section, or even that of a, which is a parabolic cube. You can do a parabolic hemisphere, which has a half circle cross section. But I'm going to skip ahead to the one that we're going to focus on, which is called the disk method. And the disk method is what we are going to use here in our cone when we run it through calculus. The disk method occurs and is called such because each of these cross sections represent a disk. If you think about old CDs, they were perfect circles, and you stack them on top of each other, so you can each of these represents a different sized CD or a different sized disk. And because they are disks, all of them using the disk method, your area is going to be that of a circle. So let's take a look at the disk method first about the x-axis. And then we're going to use that to see if we can get the same area for our cone. So let me write it out first. So if we're doing the disk method about the x-axis, of course, you're going to let f be a continuous function with f of x greater than or equal to 0 on some interval a to b. Okay, and if the region R bounded by the graph, I'm giving you the formal definition here. and the x-axis, and the lines x equaling a, these are our boundaries, and x equaling b, is revolved about the x-axis. Then the resulting solid of revolution, that's what this is called, a solid of revolution, is, now remember, we are doing ones that very specifically have circles as their slices. So we can adjust our general slicing method a little bit because the area is going to be that of a circle. So the volume equals the integral from A to B. So what is the area of a circle? Area of a circle is pi r squared. So it's pi. Now, how did we get r? R depends on our function. So whatever x is, we use our function to get r, to get our f of x. So r, which is squared, now f of x is squared dx. And that is the formula for the disk method when you revolve a function about the x-axis. So let's go back to our cone and apply it. I'll draw a small cone picture down here. Remember, so I'll change it to f of x. Let's make sure we're using the same 1/2 x. Remember, we got 16/3 pi, so we're hoping to get the same thing. So it's 1/2 x and taken to 4. And our function goes to, hold on, to 4. All right, so plugging it into our disk method, revolving around the x-axis, to get our volume, we're going to go from 0 to 4 pi 1/2 x squared dx. And we're simply going to quickly solve this. So what does that give me? Pi. So 1/2 x squared, which is 1/4 x squared. So it ends up being x cubed over 12, correct? Because yeah, so that should be over 12 from 0 to 4. So that's going to give us pi times, so 4 cubed is 64 over 12 minus 0. 64 over 12, if you divide by 4, you get 16 pi over 3. Okay, which is exactly what we got up here. Now, clearly, if your figure comes out to a nice geometric and you know the area, you can simply use your geometric formula for that. But as we're going to see in a minute, we're going to do figures that are not nice, neat geometric figures. Okay, so I'm going to grab an example out of the textbook, but I'll do, let's do this one. Suppose we haven't done anything with e yet, so let's do e to the negative x. And of course, y equals 0 and x equals 0. To x equals ln 4, and we're going to go about, we're going to rotate it about the x-axis. And we're going to talk about that in a minute. You're always going to be given which axis to rotate. Keep that in mind. So what does this look like? Well, if you remember your e of x function, ln4 will be around here somewhere. It's going to come down something like this, right? We're going to stop it. So it's going to keep going. It's going to keep going up. We're going to do here. Now, of course, this is going to get rotated, and as you can imagine, it's going to look kind of funky, right? It's going to go like this. Your circles are going to kind of be like this. There's your discs. There are, you know, various discs as you go through. So we're going to go ahead and confirm, yes, they're circles. Yes, we can just use our general disk method. And we just got to get the area. We're going to add up the area of infinitely many of these circles. So to do that, we have to go from 0 to ln4. All right, so area of each circle is pi r squared. R is simply going to be represented by your f of x. So our f of x is e to the negative x squared dx. All right, that's our function. So all we need to do, and that's our integral, all we need to do is integrate that, which is not too hard. You know, you can always throw the pi out here if you don't want to deal with it. So that's e to the negative 2x dx. I just took e to the negative x and raised it to the second power. I'm going to do a shortened version of u sub here because this is pretty easy. We know if we let u be negative 2x, again, when I say a shortened version, I'm not going to do all the u sub. I know what I really need for this to work is a negative 2 out front. And I don't have a negative 2, so I'm going to put it divide by negative 2 over here. Basic u sub information. In doing that, all I have to do then is integrate e to the 2x, which is e to the negative 2x. I'm not going to change everything to u's. It actually gets a little more complicated in this problem. You can certainly try it. Again, I'm going to kind of go through some of this u substitution quickly, but basically that's what I did. I let u be, and du is negative 2 dx. All right, so I need a negative 2 technically in here, and I balance that with a negative 2 out there. That's the idea behind it. I'm just skipping some of the steps at this point. And we're going to integrate that from 0 to ln4, because again, I don't want to change my limits in this case. They're going to work very nicely with the e. All right, so negative, I don't know why I have 2 negatives on that one. Should only have 1 negative. Negative pi over 2. So I have e to the negative 2 ln4 minus e to the 0. All right, well, you can use your calculator, of course, but you really don't need to for this problem. Okay, the negative 2, so let's just take this and scoot it out of the problem for a second. E to the negative 2 ln4 is the same as e to the negative 2 power. I just used one of the logarithmic rules, which is e. Oh, no, we don't even need the e because the e's and the ln's pretty much cancel each other out, which is 1/16. That's all it comes out to. So again, didn't need a calculator, but you can use yours. Minus 1. So it's negative pi over 2. It's 1/16 minus 16/16 is going to be negative, negative 15 over 16. So what do we have? We have 15 pi over 32. Okay. Now, as we found in the last section, there's going to be a lot of variations, of course, on this. This is just the very simple disk around the x-axis. I don't have to only rotate around the x-axis. I can rotate my function around the y-axis. So what would that look like? Well, your disk method it's going to be very similar to this function. All right, very similar indeed. The difference is the volume is now equal to, we're going to change it to C and D. And instead of using an f of x, let's use a p of x. And it wouldn't be of x. So let's suppose that p of y is a continuous function. And R is the region bounded by my P of Y. And Y equals C, Y equals D. When R is revolved around the y-axis, you're going to go from C to D. Still going to make a circle, so you still have pi r squared, but your R now is represented by P of Y squared dy. So your function has to be solved for x for it to be a P of Y function. Keep that in mind. Let's try one of those examples. And I'm going to do something a little similar. This is number 22 in the textbook. I'll always try to do odd problems in the textbook because I want to leave the even ones for you to try on your own, because your student solution manual in Math Lab will always have all the fully worked out solutions to the even problems. So let me try 22. And the reason I'm picking this one, so this one says y equals 0, y equals ln x, y equals 2, x equals 0. And we want to take this and revolve it, all these boundary lines, and we revolve it around the y-axis. And there's a picture in your textbook as well, so you can kind of see what's going on. So here we have our y-axis. It's an ln function, which is a pretty basic function. It goes through 1 and looks something like this, right? There's your ln function. We're going to do this function from y equaling 0 to y equaling 2. So here's y equaling 0. So let's think about what it's bounded by here. I'll do that in red for a second. It's bounded by y equals 0, y equals ln x, y equals 2, and x equals 0, so here. So we're taking this and we're going to go ahead and revolve it around the y-axis. So keep in mind, when you do that revolution around the y-axis, right, you're going to come out. Let's see, it's going to come out here. It's going to go like this, right? And your circles are actually this way, right? These are your disks, your infinitely many disks, each with a radius, okay? So that's what we're going to utilize. And this is going to be pretty important when you come up to the next section in 6.4 and we look at another method. When you're revolving around the y, your kind of little rectangles, your circles, are perpendicular to the y-axis. When we revolved around the x, we were perpendicular to the x-axis, and that's going to be something to keep in mind later. And this is true for the disk method. All right. Well, okay, there was my formula right there. Volume equals, so C to D. There's my C. There's my D. I'm going to go from 0 to 2. of pi. We've clarified these are definitely circles. Oh, wait, I can't plug in. So here's the other thing. A common mistake might be, and don't write this down, this is going to be a mistake, ln x dy. Yeah, that doesn't work. You can't have a function with an x in it when you need to differentiate with respect to y. That's a big no-no. So where's our issue? Right here. You have y equals ln x. You can't have y equals ln x. You got to solve for x. So to solve for x, you're going to end up with e to the y. All right? Equals x. You just switch it around so you're solved for x. And the reciprocal function, of course, is ln is e to the y. Of ln x is e to the y. So you can go ahead and put in e to the y, and of course that e to the y gets squared, which means it's 0 to 2. Let's pop the pi out. E to y dy. I'm going to do, again, a very, very quick u sub here. I'm not going to go through the process. It's going to work very much like the other one we did. You're going to need a division of 2. And then we can say the integral of the 2y is simply 2y because I've got that division of 2 over there to compensate. And I'm going to go from 0 to 2, which is pi over 2. E to the 4 is just e to the 4. And e to the 0 minus is 1. Because e to the 0 power is 1. So that's your answer. Nothing else to be done there. So you can differentiate with respect around, you can differentiate, or you can revolve it around the y-axis. And if you do that in the disk method, you then differentiate with respect to y. Now, we can also add another little twist to these functions. Okay, so the next one I want to do is number 24 from the text. And number 24 gives us y, and this will lead us into the last part of this particular section. And you'll kind of see what it is in a minute when you see the graph. So if we have the function y equals x, and then we have y equals 4th root of x, and we're just going to simply revolve that around the x-axis. So again, really important to see what we're revolving around. This one we did the y-axis. We're going to do the x-axis on this one. So let's get a look at what these functions look like. Notice right off the bat, I am not bounded by either the x or the y-axis. Okay. All right, so y equals x. So there's my y equals x function. And y equals the 4th root of x is kind of like a wider parabola, for lack of a better term. Okay. So we have our wider parabola there. Oh, yeah. So I'm going to revolve this around the x-axis. Well, when I do that, I'm going to get another y equals x. I'm going to finish that. And let's see if we can figure this out, because we'll have this kind of outer circle, if you can imagine it. And then we'll have this inner circle for each slice. We actually end up with definitely not a disk. This is what we would refer to as a washer. All right. So if you can picture it, it's kind of hollowed out in the middle. It is not a full disk. It's a washer, like those little things you put when you, I don't know, nuts and bolts. They got washers that go with them before you hammer them into the wood. So when we're dealing with a washer, so let's take one moment before we come back to this problem and discuss for a second the washer method. And this is very similar to when we talk about area between two curves. As you can imagine, what we're doing is finding the full area of the outer circle and subtracting away that area of the inner circle. And that's exactly what it ends up looking like. So when we take the washer method, let's go first, washer method, and we'll go about the x-axis. And I'm not going to write all that stuff on top. You can get an idea what's written there. What does our volume look like? It's going to be the area from A to B, because that's what we're bounded by. We're still dealing with circles. All right. The difference is we have to subtract those radius. So we can do pi so this one represents, of course, the outer radius, and you need to subtract away the inner radius. And all I did was, you know, you can distribute the pi and have it in front of each, but I put it on the outside. Of course, if this was about the y-axis, it would be very similar, but we would go from C to D. And let's use P of y squared minus Q of y squared, and it would be a dy. So, you know, to understand this, you have to get a picture of what these graphs look like. And if the picture's not giving to you, say on a lab or on one of your math lab, you can go into Desmos. On a test, unless it's blatantly obvious, I will draw out that picture for you so you can see it. All right, so that being said, we can finish this problem off. So we're going to take the integral up. So we need to know how far out we're going. That piece is missing. Obviously, we're starting at 0. And this is just where does x equal the 4th root of x. Sorry. So you always figure this out by setting them equal to each other. There's different ways of doing this, but clearly you don't really have to do much math here. You can see that it's only going to work when x equals 1. It's the only time the 4th root of x is going to be equal to x itself, is when x is 1. So this is going to go from 0 to 1. Right, so we have our pi. So our outer circle is the function y equals the 4th root of x, but we have to square it. So we have the 4th root of x squared. The inner function, which is right here, is going to just be x squared dx. Let's clean it up a little bit. Move the pi out front. If you take the 4th root and you square it, you end up with the square root. And I'm actually going to change that and write my square root as x to the 1/2. Right, so now we have pi, and so it's 2/3 x to the 3/2 minus x to the 3rd over 3. I'll let you play around and do all that fun math, and your answer should come out to pi over 3. Okay? So this should give you a nice little start to volumes by slicing, using your disc or washer. What the picture looks like is what determines whether you're using a disc or a washer. Clearly, if you have this hole, you have to use your washer method. You've got to subtract them But in the other functions, when they went right up to the axis, then you're able to use the disk method. Now, whether or not you revolve it around the y or the x-axis, that's going to be given to you in the problem, so you don't need to necessarily think about that. Just be careful. As I stated in this problem here, make sure you change your function so it's solved for the correct variable. Okay? And that's it for 6.3. And as always, you can go into the MathLab videos if you want to see some more examples or take a look at the PowerPoint slides that are in Canvas.